Which one? Oh, that is the last part because tomorrow I plan to be tomorrow to do exercises only, or to do a big ramp up. But I noticed today that I cannot do the revision section next week because I'm going to be away. So I could leave you the choice whether to do in the hour tomorrow, the hour before the workshop. I can leave you the choice whether to do the revision section, which is basically going to be simply this is what we have done in my part of the course, and what you expect for the exam. But I would probably prefer to do exercises because you are sure 100% that a lot of retrosynthesis is going to be in your exam, both for me and for Smarty. So I prefer to do exercise. But if you tomorrow decide that you prefer to have a revision session, try to get also the parts to revise, not to revise, but just to wrap up, to summarize what we have done in retrosynthesis, but also cross-coupling, but also pericyclic and the spectroscopy, then we can do it. I think, in my experience, I don't think that revision section is super useful. It could be useful up to level because it reminds you of whatever we've done. But at the same time, you know what we've done. So technically speaking, there is really no need for doing that because you expect I know you expect examples, exercises of both retrosynthesis and also cross-coupling and also a little bit of pericyclic reaction. So, but you tell me tomorrow. Today, anyway, whatever we do today is I want to finish with something that we've done partly last year, but now we're doing a little more, let's say more advanced one. It's not too advanced. It's just because we put also the other functional groups together. And these are, the first hour we'll do 1,3 and 1,5 dicarbonyls. And I kept saying that carbonyls are the most useful and most versatile functional groups that you can use in retrosynthesis and solid synthesis. But also because, it sometimes gets you out of trouble. So if you don't know exactly what to do in a certain part of a molecule, you can always start from something which reminds you of a carbonyl, and maybe you take it out later if you need to. But maybe if the chemistry of the carbonyls is more familiar to you, it's easier to start with that instead of starting from a different side of the molecule for them. But 1,3, 1,5 are the ones that normally are considered the more the reaction with the dicarbonyl chemistry, carbonyl chemistry in general, the reactions are the more natural. So when you use the more natural tendency of the carbonyl to do a certain kind of reactions. Like we were discussing this morning in the workshop. You use your benzene as your nucleophile normally, apart from certain selected cases. The same is for the carbonyl. Normally, you use the carbonyl for specific reasons. Either you like the carbonyl itself, so you use it as an electrophile, or if you need to use it as a nucleophile, you go through the innovate. Try to remember all the chemistry for the synthesis of aromatic heterocycles, for instance. So all the carbonyl chemistry can be used either from the lipophilic point of view or from the electrophilic. So this is a very short, very short wrap-up of the chemistry of 1,3 and 1,5 dicarbonyl. I'm going to give you in tomorrow's session and for the revision. So I prefer to do it tomorrow at the very start. I'm going to give you some slides that you can find on Canvas anyway, where I gather the most useful, the most recurrent reactions of each functional group. Okay, so that can be used as a template for your retrosynthesis. It's not comprehensive by all means. So that doesn't mean that whatever molecule you have can be solved using these kind of methods. But those are pretty common. So I'm going to give you all the different tables. Use them because at least if you know something like that, if you can use all these kind of compounds and the chemistry related to this kind of compounds, you know what to do in case you either see 1,3 or 1,5 in this case, that carbonyl connection, or you can put yourself in the condition there is 1,3, 1,5, adding or removing carbonyls using FGIs and so on. Okay. So normally those are the 1,3 and 1,5 are the easiest one to disconnect. Let's do the 1,3 first, but very quickly. Normally on the 1,3, you use one part of the molecule. If you disconnect between the two carbons, you use one part of the molecule which has the nucleophile part, the nucleophilic part, and the other part which is the electrophilic. Clearly, like I was saying, the nucleophilic part could be your enolate, so one molecule which has alpha protons, and that can be turned into a nucleophile, an enolate. Or on the other side, you must use a compound which has the carbonyl as an electrophile. And normally, if you want to keep the carbonyl, you must have a leaving group next to it. Because if you don't have a leaving group, instead of substitution of the carbonyl, so that restores the carbonyl, you will have addition and you will get the hydroxyl. Sometimes you want to do that because maybe you need the alcohol. But in the case of the 1,3 and the 1,5, you must keep the carbonyl. So if you want to have anything which has a carbonyl and you want to keep it on a carbonyl, if it reacts here on the delta plus using the carbonyl as an electrophile, if you want to restore the carbonyl, you must have a good leaving group. And the reason is, whatever nucleophile, if you attack here, it breaks the carbonyl. If it breaks the carbonyl, you automatically get the alkoxide. Even not doing step by step, if you get O minus here, if it wants to go back to carbonyl, so you can restore the carbonyl, it has to do that, kicking out a leaving group. So if you don't have a good leaving group, that reaction won't happen. That means if you have a nucleophile, and let's say you have an aldehyde, let's say acetaldehyde. You do that, yes, it works. The aldehyde is a very good electrophile. The carbonyl of the aldehyde is a very good electrophile. But it stops here because you get your nucleophile, your alkoxide. This was the proton of the aldehyde. It doesn't leave. The proton, the hydride, as a leaving group is no good. That's why you never, ever do Fourier crafts with aldehydes as well, because the hydride is not a leaving group. If you want to keep the carbonyl, you must have a leaving group next to the carbonyl. It could be a chloride, it could be from a anhydride, it could be even an ester. But it must be a good leaving group. Okay? We will see the 1,5 after that. The 1,5 relies on the attack of the same nucleophile. So if you have the same nucleophile as that, if your nucleophile is your enolate, or if you prefer even better, this form. If you have this nucleophile here, if you want to create a 1,5 relationship, you must have a conjugated molecule like that, so that the soft nucleophile does Michael addition. We will see with examples, but don't worry. But the rules of 1,3 is one side enolate, one side carbonyl with leaving group. The rule of the 1,5 is, what you need to remember for the 1,5 point of view is enolate on one side, alpha, beta, unsaturated carbonyl on the other side, so you can do Michael addition instead of direct attack on the carbon. Let's see with examples. Useful of the enolates. Why the enolates? Why we banged on so much, both me and Joel, and pretty sure also Sumati did that. Why do we bang down so much on alpha protons? Whatever is Z, if you have alpha protons, you can use a base to take one of the alpha protons, which is relatively acidic, and you can form your enolate. I prefer, from the mechanistic point of view, I prefer the bottom one. From the retrosynthesis point of view, I don't care too much because I'm not going to ask you the mechanism. But if you know, and if you can imagine the mechanism, you know automatically the reactivity. So this is the enolate. If you add to the enolate any electrophile, it will work. For instance, if you add bromide, which is the same reaction that you'll do on a benzene ring, you can add bromide to the enolate. You can do normal SN2 reactions. Let's say methyl iodide is one of the most typical way to do an SN2. The enolate is nucleophilic enough to do SN2 and kicking out the iodide. You can do this kind of reactions like I was saying here. If you don't have a living group, you keep the alcohol. If you do have a living group, you keep the carbonyl. Whatever the living group is, you can keep the carbonyl, and you can do, for instance, the first reaction, one of the carbonyl reactions. You can also, and this is something that I recall very briefly, you did with Joe sometimes, last year you did with Joe for sure. Sometimes you need to tame the enolate, so you block the enolate in this position, just so that in this case, it reacts very quickly with another molecule and less with itself. Sometimes you need to block the enolate to tame the enolate because you don't want that it reacts with itself. But this is another way to still to use the enolate. So it's not particularly different. So any of those reactions, whether you do 1,3-dicarbonyls or 1,5-dicarbonyls, you will use, because one of them is definitely the use of, on one side is definitely the use of the alpha protons next to the carbonyl, okay? Remember that some of those, they can still have alpha protons, so from the economy of your retrosynthesis, you might still continue using them. We saw that in the synthesis of heterocycles very often. We create something which has alpha protons, but in the next molecule, you still have alpha protons that can be used and will be used. Okay, so the chemistry of alpha protons is so useful for retrosynthesis in general. Now, example, this is the target molecule. Think about how do you make it? This is a 1,3-dicarbonyl relationship. So considering that you can cut either on one side or the other of the carbonyl. So from carbonyl on the left or from carbonyl on the right. What would you do from the column of your promoter flask? Let's say that you are in the lab. Where do you start? Which carbon to connect? Left or right? Right, right? So not complete right, no, I'm talking about in between the two carbonyls. Let's focus on the 1,3-dicarbonyl. Then you are not wrong, because if you're starting this connection, you can start from that point of view. But here we're talking about 1,3, so let's focus on the 1,3. Still right. On the right, from the carbonyl on the right, or the carbonyl on the left. If you cut in the middle, you're breaking the 5-member ring. And if you disconnect on the side of a carbonyl, remember that if you want to use nucleophile, which is an enolate, which has alpha protons, on the other side, there must be a living group. So you put, as a synthetic equivalent, something with an ester. It could be a chloride. In this case, I chose an ester. As it's easier to make ester because this molecule becomes very symmetrical. The synthesis will simply be, if you have this molecule, you put a base, whatever alpha proton you take, you see that there are alpha protons only on one side, but the molecule is symmetrical. That's why probably in this molecule, it might sound a little bit counterintuitive. You can indeed keep the 5-member ring and react with a diester. The problem on reacting with the diester will be if you cut on the other side and you get the negative charge here, alpha protons, fine. The problem here is that on the other side, since you have to keep the carbonyl, you need to put something like that. And this compound is quite unstable. So if you have to do it in the lab, the spite on the paper is still absolutely fine. In the lab, probably I would prefer to do this way. Again, this way using the data here, so that this one goes up and it kicks out one of the toxic groups, still fine, still works. So it's not a wrong answer. Probably I would prefer to do this way. This reaction, if you remember names, is called Dickmann condensation. It's a variation of the Claisen because the Claisen is a condensation of an enolate with an ester. In this case, the Dickmann is intramolecular, but the chemistry is absolutely the same. Alpha protons, they kick out an ester group, keeping a carbon. What about this one? Two. 1, 2, 3, dicarbonyl, 1, 2, 3, dicarbonyl. So you can choose which type of carbon. So you have this molecule. Where would you start from? Let's say that you do this way. It's doable. I would say that this molecule is pretty unstable, but it is doable. What about acidity of this compound? So this compound is very, very acidic. So it's taken much more easily than any other alpha proton. Then you put an acyl chloride, or you could put another ester on the other side, and that reaction, technically speaking, works. This diacetyl is not particularly stable, but it's still doable. If you want to cut them, you can still use the acidity of this alpha proton, and you can do an SN2 reaction on this benzene bromide. So you see, as always, we can solve nasty problems sometimes with simple reactions. Alpha protons, SN2, all reactions that we've done throughout first, second, and third year, normally it's easy enough to do. Synthesis. The synthesis sometimes it might be straightforward and might be more complicated. Remember that the synthesis, you need to tell me if there are reagents, particular reagents and conditions. In the retrosynthesis, you don't. So sometimes in the synthesis, you also tell me if you need to do activation or protection groups. In the retrosynthesis, you don't. So that's a very easy one. These protons are very acidic. Even a mild base will take it out. SN2, the benzyl bromide is incredibly reactive. Same reason. This delta plus here has a delta minus, a strong delta minus from the bromide point of view, and has another strong delta minus because of the electron density pool of the benzene ring. Apart from that, yes, if you put another base quickly, and this acyl chloride, it will give you your right molecule. Not particularly nice molecule, but on the paper, it's very good to play with. Okay, give you a little more time to do this. Try to practice, because these reactions are the ones that you are starting putting different functional groups are getting closer and closer to something you might have an example. From my point of view, the strategy will be still circle all the functional groups and think about, okay, here I have what? An hydroxyl group, carbonyl group, which is an ester, an aromatic group, an amino group. You know more or less how to include amino groups. You know more or less how to create hydroxyl groups. how to use aromatic chemistry. It's just a matter of starting from the most efficient way, and the most efficient point of view. Think about this molecule a bit. Any ideas? So you can expect tomorrow workshop to have this kind of level of difficulty, and don't go much over that. Don't expect anything much more complicated than that. But we still have lots of functional groups to play with, and technically speaking, lots of different ways you can approach this one. Any ideas where to start? Disconnect the benzene. Or if you disconnect the benzene, what are the synthetic equivalents? How do you then reattach the benzene in synthesis? I'm not saying that it's wrong. The ester is a very good option because the formation of an ester is a very easy one and very selective if you have an acyl chloride or even another ester. So the ester could be a very good option. You have also an hydroxyl. What would you use to create that hydroxyl here? You can imagine having a carbonyl, which doesn't have a leaving group, because if you keep the 5-member ring, any of the carbons next to the carbonyl are not good leaving groups. So if you do anything that as a nucleophile attaches to that carbonyl, then will leave the hydroxyl group behind. So you see, there are all considerations that you can do. It's just a matter of choosing one order of reactivity. So let's say that you start from the ester, because the ester is probably, like we said, is the easiest reaction probably in terms of synthesis. So this is a very good way to start your retrosynthesis. So then you have this molecule. Yeah, you can use cyclopentanol. Anything with alpha protons is good enough to attack the carbonyl and leaves the hydroxyl behind. It doesn't reform the carbonyl because they are not leaving groups. This one, how can you make it? It's not a benzoic acid. Benzoic acid is the carboxyl is connected straight to the aromatic group. This one has a carbon next to it, so we need to do it in a way. You can do an FGI. You can do carboxylic acid. In this one, you need to think about how do I normally make carboxylic acid. Common one is greener than CO2, but also using the nitrile, and hydrolysis of nitriles gives you carboxylic acid. It could come from an epoxide, which forms the alcohol, and then oxidation of the alcohol to carboxylic acid. Let's see. So this one, what I chose is esterification. It might sound counterintuitive. What I chose in this one is esterification first, so that from the carboxylic acid you form an ester, which is a little easier to handle. And then on this one, you do first your enolate, so taking out one of the alpha protons from here. It's easy because we don't have any alpha protons. So one base will work, any base will work. You can use this one. Then on this one, on the hydroxyl, you can do a simple trans esterification. So instead of doing the esterification straight from the carboxylic acid and an alcohol, in this case, an hydroxylamine, sometimes it's easier if you actually start from the ester and you do a trans esterification, because this one is actually a much better living group than water that you will have if you have the carboxylic acid. But let's say that if you told me, at the example, at the workshop, if you told me that you start from the carboxylic acid straight away and you do a normal esterification in acid conditions, they will do. There is only one problem, and that's why I prefer this route. Can you see why I don't prefer? I prefer using basic conditions like this one instead of acidic conditions and doing from the acid, if this one was an acid, straight to the ester. There is one reason why it's so much better this way and very dangerous from the chemistry point of view. If I have an acid here, I use this alcohol to do esterification in acidic conditions. What could happen to this molecule? What happens very labile in acidic conditions? Anyone? Look at the molecule. What could be labile in acidic conditions? The alcohol will leave water. If you protonate that alcohol in the same moment that you protonate the carbonyl to activate it in acidic conditions, if you protonate this alcohol and if this one leaves, where do you put the double bond? You put the double bond conjugated to carbonyl. We know that this is a strong driving force. If you can do conjugation, the conjugation to the dehydration by conjugation, because of conjugation, is so good that if you do E1CB, you can kick out even an hydroxide. So even in basic conditions, if you can do dehydration because of the conjugation with, in this case, the carbonyl, it will like. So if instead, from the strategic point of view, if instead you do an ester first, and then you do this one in basic conditions, worst case scenario, take out also this proton during the way, but then you restore it. And you restore it with water. You don't need a strong acid to restore it, so you can keep it. If this one forms a double bond here, it's conjugated to this carbonyl, but it's also conjugated with the aromatic ring. I will say that this hydroxyl group is quite unstable. It really wants to leave. Don't give it a better chance to leave. Okay? So again, think about the possible reactions. Think about also the collateral, the problems. Let's do this one. This one is on 1.5, sorry. This one is on 1.5. It's not an exercise that we discussed yet. This one is a 1.5 dicarbonyl. We saw that briefly at the very beginning. What is the compound that you need to use to do the 1.5? On the one side is the enolate. On the other side, in order to do the 1.5, on the one side you have anything that works so that you can form your enolate. On the other side, you need an alpha beta unsaturated compound so that this reaction does micro addition or 1,4 addition, conjugate addition. So we'll go from a little bit from the 1.3 to the 1.5 now. So this one, for instance, can come from this. On the one, clearly, if you need to choose, you can have a cyclohexanol. It's a very, very stable ring. And it has two sets of alpha protons. It is symmetrical. So you don't even care about kinetic or thermodynamic condition. So you keep the enolate on this side. On the other side, you could do something like that also. If you know you have to attack here, not here, you could imagine putting a chloride or a bromide, because this is delta minus, this is delta plus. They will do the same reaction as the conjugate addition, so we'll give you the same product. But this one is much more difficult to synthesize. If you need to carry on with the retrosynthesis, this one is more problematic than actually preparing double bonds and making that alpha beta unsaturated carbon. Okay. That's synthesis, LDA, why not? You might need to change the enolate. This is always true. And the reason is always the same. If you need to change the enolate, it's not normally to prevent condensation. So you form the base, you form the enolate, instead of attacking the other molecule, maybe it prefers to attack itself. But let's say that a very lenient example. I don't expect you to always remember, maybe I need to change the enolate to protect the enolate in this case. I prefer that you know the strategy rather than you know all different tricks that you will actually do in the lab. Then you do 1,4 attack. It's a soft nucleophile. You know that if you remember, conjugate attack is mainly done by soft nucleophiles because the hard nucleophiles will attack the carbonyl. If you want to attack 1,4, you must have a soft nucleophile. And the enolate is one of the most typical soft nucleophile you can find. So this will create your molecule nice and easy. A little more complicated. Let's do this way. Let's talk about how to put the amino group, but hopefully you remember. I don't want to do everything because otherwise it will take forever. But also think about how to, if you want to keep disconnecting the alpha beta unsaturated carbonyl, think about how to do it. Let's focus on this new target molecule now. This is slightly more complicated because it might not be, the best strategy might not be as intuitive as others. So what would we disconnect? It's a nice one. I like this molecule because you see the 1,3 disconnection, but I would not start from the 1,3 from the strategic point of view. What would you start your disconnection here? What do you think? You can say always, you can start from the ester, that's the easy way, but then you get a carboxylic acid. It doesn't help you too much in the rest of this connection. So you can do it at first, you can do it later, but this one, it's a nice and easy one. Let's focus on the most difficult part. You can do a 1,3 disconnection and you disconnect here or disconnect there. But actually I wouldn't start from that. I would start from disconnecting this one and then do 1,5 instead, especially because we're doing 1,5. So if you do disconnect from this double bond, whenever you see a double bond, we saw that when we did alkenes. Whenever you see a double bond, 90% of the times, the double bond comes from a direct attack on a carbonyl, which didn't have a living group, creates a hydroxyl, and then you need to take out water. Most of the double bonds are formed by dehydration. The other double bonds, the other easy way to form double bonds, we saw that is with Vitic. Probably I wouldn't do Vitic in here, but you could. I will start the disconnection simply by having in mind the fact that the double bond is there because at some point you remove water. If you remove water and you attack the carbonyl, it means that, like we saw before, the carbonyl doesn't have a good living group. So you form the alcohol. If it conjugates with something else, we saw that before, it forms the double bond very, very efficiently. So the ring closure, if you put a base in this compound, you need to consider that the number of alpha protons you have. Alpha protons here, alpha proton there, alpha protons there. Here, it will do the molecule that you want. Here, will form a 4-member ring. No, no, no. Here, again, it can attack here, another 4-member ring. It can attack there, another 4-member ring. No way. You prefer to form a 6-member ring. Then this one in synthesis, that is called Robinson annulation in synthesis. Then we have a 1,5 dicarbonyl possibility. You know that if you have a 1,5 dicarbonyl, normally you disconnect in this way, and you need to put a double bond on one side and keep the enolate on the other side. Because the 1,5 dicarbonyl is always working, enolate on one side, alpha beta unsaturated carbonyl on the other. So you need to put a double bond somewhere. I will do that because it's so much easier to put a double bond here than on the other side. Sometimes it's even impossible because putting a double bond between the 1,3 is even impossible. And then you can keep disconnecting this one. In this case, yes, in this case, you have different options. Either you, again, the double bond can either come from another carbonyl which dehydrated, or in this case, you can easily also do with Wittig reactions. I would probably go for, again, this one set of alpha protons only attacks the halide, the benzoic halide, the benzyl halide. Doesn't have alpha protons on either side, so no living groups. No living groups means alcohol. Alcohol then dehydrates, conjugated with this, which is conjugated with that, conjugated with the benzyl. Super, almost impossible to keep the alcohol on this carbon. Almost impossible, because it dehydrates so easily because it's conjugated with everything. What about the synthesis? So here, three problems in synthesis, because whenever you do retrosynthesis, you always need to consider, does this reaction work in synthesis? All the steps are in the wrong order and the right order. Think about all potential collateral problems. This one set of alpha protons, aldehyde much more electrophilic than this carbonyl anyway, so probably this one will react even if you do not change the enolate. Because as soon as it forms the enolate, it attacks the more electrophilic carbonyl. Then dehydration. I'm not doing this, but again, dehydration here will remove or something which eventually is conjugated with another aromatic ring. So dehydration here is so easy that probably it's even difficult to keep it. Then you have, in this case, two sets of alpha protons. But can you be selective? Which set of alpha protons is more acidic or the other side? One is definitely more acidic. Why? In between the carbons. Easy. Okay? Hopefully it's easy. I hope that by now it's easy. Then one driving force, apart from the potential formation of four-member rings versus a six-member ring, which is much more stable. The other driving force is that this reaction is intramolecular. So the reaction that eventually forms your target molecule is super easy because it's intramolecular, and it's super easy because, again, the double bond that you're going to form is conjugated with both the carbonyl and the phenyl ring. So that's the best strategy. So even if you think, I see immediately a 1,3 dicarbonyl relationship, sometimes it's easier to start working on the other side. Because if you do this right here, you can have this one with a living group. This molecule, we already know that it's quite unstable because this living group is pulling electron density. This oxygen is also pulling electron density. This compound is super unstable. Super unstable means also super reactive. You may react with a lot of other things. But then you need to disconnect here. And now, if you disconnect on the side and you get a carbon here, it's still good, but it's not as good as the one you did before. The point is, again, if you do that, I don't like it particularly, but if you start from this route at the exam or at the workshop, and eventually you can do a forward synthesis, which is plausible, is good to me. It doesn't matter that I choose a different pathway. If you still prove that in my work, it leads to more, I don't know, side reactions in your bottom flask. But if it's still good in terms of doable, I'm happy. This one should be easier. Or is it? Looks easier. It's a smaller molecule. Don't get confused by the smaller molecules, because sometimes when you have a larger molecule like the one that we had before, they have so many different points to attack, and you can find different routes that can be still doable. With a smaller molecule, sometimes you don't have that luxury. You must work with the functional groups you have. So, what do you do? Any ideas? To get the first. Okay, we're using what? CC, disconnect. Okay, there are many CCs. So between the aromatic and the aliphatic chain. But then we will get dicarbonyl after the post conversion. If you work from the 1,5 dicarbonyl point of view, you can disconnect either part that I got in red. So if you disconnect in that side, you need to put the double bond somewhere. Where do you put your double bond? This is a reaction that I will do this way. Oh. Okay, yeah, I see. That aromatic sometimes, the aromatic chemistry is so useful, but sometimes it leads you to the wrong answers. So attacking the aromatic straight away to the aliphatic chain would be impossible. Doing the proper 1,5 will also be very difficult. Because if you do a proper 1,5, you get something like that, plus your aromatic group. That is a 1,5. You create uranolate, and then you work this way. But it's not that easy. Instead, if you do this one on the haldehyde, eventually you go back to anisole. It's not as easy as it seems sometimes. So, very quickly to get the haldehyde from the anisole, the methoxybenzene, you can brominate. Then you do one of the typical reactions to put the carboxylic acid. Once you get the carboxylic acid, there are not many reagents that actually can go from the carboxylic acid and reduce it to the aldehyde. The aldehyde is a trick one because it's too reactive. So when you do reductions of carboxylic acid, you might go straight away to alcohol. The same way, when you do oxidation of alcohol, sometimes it doesn't stop aldehyde, it goes straight away to carboxylic acid. So there are not many reagents that form that forms a aldehyde. One of them is, if you start from the ester, is Dibal-H. Dibal-H is one of those boron reducing agents, but it's very, very bulky. And because it's very, very bulky, instead of carry on with the reduction, it stops. You can, with Dibal-H, actually stop aldehyde. Instead of, if you do with sodium boride, it will definitely go to alcohol. Dibal-H, this is one of the reagents that you really need if you do this kind of reduction. But example, you need to tell me what kind of reducing agent you use. Normally, I will accept lithium aluminum hydride, sodium boride. In this case, if you want to stop the aldehyde, you need to tell me how you stop the aldehyde. Because you do need the aldehyde. Because when you do this reaction with the aldehyde, you form this compound that you actually need for doing your 1,5. To do the 1,5 dicarbonyl, you need the alpha beta saturated. So if you attack the aldehyde there, if you attack the aldehyde with the enolate, say also after protonation, let's say with water. Now, at this point, by dehydration, you can definitely form the double bond in the position that you need. Now you do this reaction again with acetone. That's why there was 2 per acetone. Now, if you stop here, you isolate this compound, and you do the next reaction, then if immediately you can do the typical micro addition. So if you do the 1,5 step by step, you get these two. Now you need to disconnect this one. If you want to disconnect this one, and you start here, the double bond must come from aldehyde. Then you need to think about how to make the aldehyde. Making aldehyde is not that easy, but it's doable. Totally doable. Okay? In synthesis, of course, carry on. This one. Does it really work? There are so many if and buts. If you are in the lab, I will say that it's not that easy because aldehydes are nasty. Well, not nasty in terms of toxicity or super high reactivity, are very difficult sometimes to stop to the aldehyde. You can also do with this one. This one actually has this alpha proton, which are in between 2 carbonyls, much more acidic, and probably you can get away. So what I'm doing here, that is something that you might want to mention only when you do the full one synthesis, is that you use an activating group. How do you remove this ester group? You can remove this ester group. We saw that already. Only if it's in 1, 2, 3 position to the carbonyl, you can saturate this bond. And that is the capture reaction. Alternatively, if you don't want to do the capture, so if you don't remember, then lithium chloride or sodium chloride and DMSO straight from the ester, you can do hydrolysis of the ester and thermal decarboxylation. If you remove this ester, if you don't remember the capture, you remove this ester from the relative carboxylic acid, and then you heat up the temperature, you put up the temperature, you will get thermal decarboxylation. They're equally good to me. Again, if you did that with 2 acetone at a time, probably I will forgive you because it's not an easy one. If instead you do that with the activation group, I will be much happier. Because if you are in the lab, this is what I will do. But again, I try to get the best out of each reaction. So if you can work it out doing the first part of your reaction, going step by step using the 1,5 dicarbonyl, it will still do to me. I will stop for a moment and then we'll do 1,4,1,6. Let's do a little break. And then we'll do the very last one because the 1,4,1,6 are from the retrosynthesis point of view. Apart from tomorrow, that we have exercises and workshop. But anyway, 1, 2, 1, 4, and 1, 6. We said that the 1, 3, and 1, 5 were the easier to disconnect, but again, you can do a lot of things. 1, 2, 1, 4, and 1, 6. If you remember the even numbers in terms of dicarbonyls, they are the more they call illogical disconnection. So this is another part of the slide that I'm going to give you. Let's focus in here only on the 1, 2, 1, 4, and 1, 6. 1, 6, very unlikely. We saw the 1, 6 before it was the Robertson formulation. 1, 6 are probably, let's say, I probably shouldn't say that, but from a strategic point of view, probably don't expect too much at exam with 1, 6. I never try to put too much on 1, 6 because they're the most illogical to me. The reconnections, they are the most illogical one. The one that you might want to reconnect to 1, 6 are the dual solder. So whenever you can do dual solder, remember whether you have a double bond or you don't have a double bond, you can always put, you have something like that, R, blah, 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 R prime. Even if you don't have a double bond, we saw that you can put a double bond, and then, of course, in synthesis, you need to hydrogenate. But you can always do that so that eventually you can reconnect to dual solder. One, two are to me the least intuitive because the 1, 2 required, we will see probably with a few examples. The 1, 2 are the one that requires. If you need to cut between the two carbonyls, one of them has to be your electrophile, but then you need to have another carbonyl which is a nucleophile. And the carbonyl doesn't want to be a nucleophile, the carbonyl prefers to be an electrophile. So you need to force it to become a nucleophile. There are only a couple of ways to do that. You saw that in class with me. You saw that in one of the labs last year, how to do this kind of reaction. So if I give you this one. Recognizing and you look at the lab, that one was done in this way, doing a 1, 2 dicarbonyl disconnection. They are the less intuitive to me, but since they are the less intuitive, sometimes there are only 2 ways to do that. So if you see that, you know you have to do one of these 2 ways. So there's not much to play with. The 1, 4 are probably between the 2, 1, 2, 1, 4, and 1, 6. The 1, 4 to me, from the organic synthesis point of view, are the most useful because still they are within they call illogical disconnections. But if you look at the synthetic equivalents that you need to use to do 1, 4 are actually more familiar. We use them a lot more than other things, especially the top one here. This is just something that forms an enolate, and this one is just an alpha halogenal carbonyl. Whenever you need a delta plus something somewhere, you can put just a halogen on one side, which has a strong delta minus, and it's also a very good living group. If it has a strong delta minus and it's a very good living group, leaves the positive charge behind, you know how to do it. Let's see, sometimes the relationship is not even straight away with the dicarbonyl. Sometimes it could be an hydroxo an hydroxyl and one of the carbonyls. Let's see how it works. In this case, probably you require functional group interconversion. We'll see how. Oh, for instance, you can cut here. You can have the aldehyde. The aldehyde has 1,3, suddenly 1,3 dicarbonyl relationship. So if you carry on with the retrosynthesis, you know already what to do with the 1,3. You can exploit alpha protons on one side and something with a good leaving group on the other. But since here you have to put the aldehyde, you have to leave the aldehyde, you can use these kind of compounds. So this ester, this formic ester, is very reactive. It's not the easiest one to use in the lab, but actually it gives you another very good way to put aldehydes. Let's say that it can come from the nitrile, and we will use the nitrile again to do another reaction which is very similar. And this is something very similar to what you've done in the lab. And if you have any of these formic esters, then you can do it simply by exploiting the alpha protons, any alpha protons that attack the carbonyl and that gives away the leaving group. And then the carboxylic acid can come from the bromide. You can imagine, hopefully, that coming from the bromide means Grignard reagent, CO2. This is one of the most useful ways to do that. So, again, this is probably is not the only way. By all means, it's not the only way to form carboxylic acid, but you see me using quite often this kind of chemistry because it's actually quite versatile, it's quite useful. You create your ester, then you do any base. There is only one set of alpha protons, so no problems in terms of selectivity. Anyway, any bases you create, you use your formate, the ester of the aldehyde, and you can keep the aldehyde. This is another very good way to keep the aldehyde because we saw before how difficult it is either to form the aldehyde by oxidation or the reduction. Oxidation of the alcohols normally go straight to carboxylic acid, and at the same time, reduction of alcohols normally cannot stop very easily to aldehyde, but they go automatically on full speed on the carboxylic. So at this point, you have this reaction. This is one of the few ways to do this one-two relationships. You're using sodium cyanide to form the nitrile group. You create your hydroxonitrile, and then by hydrolysis, you form your other carboxylic acid. Of course, after deprotection of nice and easy, but you don't want to use, normally, you don't want to use too much sodium cyanide. If you're doing it in the lab, there's no way that you're going to be allowed to do that. If you're going to use if you're going to do the same kind of reaction in the lab, do you remember anything which is actually quite useful, does the same, but is more user-friendly than you did it in the lab in the second year? Anyone remembers this reaction? It's still one of those which are called Ampolong reactions because you are inverting the reactivity of the carbonyl, which normally prefer to be an electrophile, but actually becomes a good nucleophile. So the Ampolongs, which we believe from German comes from what inversion of polarity, something like that. I don't know exactly the root of the word, but I know it works like that. So the Ampolong reactions can be done with the nitrites, but can be done with, do you remember what did you use on the back here? We will do that in a while, but this is what I wanted to tell you. Do you remember this one? They will do it again. you use that in the lab. This compound, which is called thiamine, is a much, much better reagent to use in the lab, much more user-friendly. It doesn't give you the the results of using any sodium cyanide or potassium cyanide. And it works exactly the same way, does exactly the same on-Paulung reaction, and you did that in the lab. At least we did the first year, the second year lab. Let's go back. This is the hydrolysis of the nitrile. This is just to show you, again, if you need a reminder, if you want to create carboxylic acid via hydrolysis of the nitrile, you do it in acidic conditions. You basically add water over and over and over again. So all these proton transfers eventually leaves you with your carboxylic acid. Now, I'm not going to ask you the mechanism for the retrosynthesis and the photosynthesis. I'm pretty sure you remember more quickly. From the nitrile, you can go to carboxylic acid. Now, exercise that I just exploded. Hopefully, you don't remember anything on that. This is still not how to make. Then you need to make the benzyl like you did in the lab. First thing, if you have this one, which is a molecule that I know quite well, I'll publish a few papers with substituted cyclopentadienos. And I can tell you that in the lab, it's a reaction that works extremely well. You have two double bonds and a carbonyl. You can imagine a double aldol condensation on this benzyl. And a double aldol condensation works extremely well in the lab. It gives you a fantastic purple-blue compound because the cyclopentadiene is so conjugated that it goes on the visible region. And if it goes well, it's one of those reactions that I always laughed when Simon said that organic is boring because they're white. You saw that you can create very nice blue compounds. This one is, depending on the substituents, goes between purple and blue. And only when it's purple or blue, you have the right compounds. Normally, when you have dark compounds in organic lab, it means you did something wrong. Not in this case. But we want to focus, apart from this one that can be done with a very nasty phosgene. Let's skip it. How do you make the benzyl? We saw that already. You did it in the lab. Normally, you do it in the benzene, starting from benzaldehyde, that whenever you did this reaction with Joel at least in 2 different labs. Whenever you all use benzaldehyde, you remember the smell of the benzaldehyde? Yes, everybody does after you do this reaction, because it contaminates 3 floors. Anything with benzaldehyde smells like almond. At the beginning it's nice, then it becomes overwhelming. So ideally, you do the same reaction with the nitrile. You invert the polarity of the carbonyl. So this carbonyl here, the carbon of this carbonyl, former carbonyl, used to be a good electropositive, a good electrophile. Now it's a very, very good nucleophile because of this on-Paulung reaction. And then you simply use the electricity of a new former carbonyl to attack another carbonyl which didn't go through the reaction. And then eventually you can have this molecule. This molecule is stable. This molecule is quite stable. So that alcohol cannot dehydrate. Don't look at it something like it's going to conjugate. It's not going to conjugate with anything. So what do? You did it in the lab. What did you do in the lab to create your benzyl? Nobody remembers? Green, no, for sure. Sorry, no. Whatever it is. Yes, but this is not. Yes.
So you just have
you have an alcohol. What can you do to get a fecal?
oxidation.
Oxidation. With what? You did it in the lab. That is a bit too harsh. Although it might work. What did you do in the lab? I'm pretty sure you did either permanganate or something with chromium, but some chromates, but probably you use permanganate. So any oxidation, if you need to do at the exam, to me, any oxidant, if you just say I need to oxidize, it will be good enough to me. The same was when you need to reduce something, if you say red will work with me, unless you need to use a specific oxidant or specific reagent, because only that oxidant or that reducing agent will do that. For instance, we saw D-H before instead of using sodium borate. Or if you want to stop the aldehyde, the carboxylic acid, D-H is the only one that really works. So if you want to do that reduction, then you need to tell me the specific reagent. Otherwise, any oxidations, any reductions, any proton transfer can be done with water. On the paper is good. But this is the stuff that I was telling you before. Thiamine, I'm not going to tell you about the mechanism of the thiamine. I'm pretty sure it was a full lab report. But we are not here for the mechanism. We're here to say just that if you remember sodium cyanide. At the exam, please use sodium cyanide, potassium cyanide, because if you write it down, it's not a good thing. Okay, more onto the dicarbonyls. So, again, if you use the haloid ring, these are your synthetic equivalents. Again, one is normal an acceptor, one is normal a donor. But if you do this reaction, normally it requires another unpooling reaction. Because if you use A1 as an acceptor, D1 again is a carbonyl, which has a negative charge, and the carbonyl normally has a positive charge instead. So either you do the same way as we did before with the natural group, or there is another typical unpooling reaction that you did with me, which is protecting the carbonyl with dithios, using butyl lithium to remove this proton. When you remove this proton, you pass from a delta plus here. When you protect here, you see, so you must go through the aldehyde. You remove this proton with butyl, then you create this compound. This compound has a strong delta minus here. It's almost a minus. It's almost a salt. It's basically a salt. So it's almost a perfect negative charge, like a grignard, like an organolithium, any other organolithium. This is an organolithium. So this one actually turns the carbon, which used to have a good delta plus, into a carbon which has a very strong delta minus. So you can do your reaction with a carbon. It's a very hard nucleophile, because now suddenly it's not even a soft nucleophile. It's like the organolithium or like Grignard reagents. They are very hard nucleophiles. So instead of attacking 1,4, it definitely attacks direct to the other carbon. So it does 1,2 attack, and then at some point you will just remove the protection group, the protecting group, thioketal, with go back to carbon. You remember how to remove it? How to remove the thioketals? You can do via very, very strong hydrolysis, because you always work. Removal of ketones in general works with strong hydrolysis, but the good thing about using sulfur groups is that with mercury salt, let's say mercury oxide or mercury chloride, both of them in neutral conditions, they remove the thioketal and they go back to carbon. This is the good news. The bad news is that everybody hates you because you use thiols, because they stink badly. But again, not in the paper. Okay, these are the 1,2. I really want to focus on those because the 1,2 are the most illogical one to me. The one that require for you to remember a little more than other reactions, because turning a carbonyl into a nucleophile is not exactly intuitive. 1,4 are easier. The 1,4, we saw that very, very briefly at the beginning, requires having one carbonyl that has your normal polarity, and the other one which has an halogen next to it. So these compounds are not that difficult to make. It's not like doing ampolong. So for example, you can do this one. From the retrosynthesis point of view, what would you start? You have carbon nitrogen, you have an ester group. If you ideally cut between the carbon and the nitrogen, because starting from the origin, something like, okay, you look at the molecule and say, okay, which is the most immediately easy to functionalize to disconnect functional group. Carbon nitrogen bonds are the easiest one. So if you immediately do that and say, okay, typical reductive amination, then in synthesis reductive amination, of course, but you can imagine you introduce that amino group ideally via reductive amination later. The reductive amination requires taking a carbonyl here. And this is 1, 2, 3, 4. So the relationship between the two carbonyls is 1,4. So whatever you can do is simply disconnect in the middle. The good thing about the 1,4, they are easier to remember to me because you always disconnect in the middle of the molecule. So you disconnect between 2 and 3, and you have these compounds, these fragments, and you can put either the negative charge on one side or on the other. It's equally good. Sometimes the choice is just a matter of which compounds gives you the best option to put the negative charge here or the positive charge there. You can invert them. Sometimes one of the choices is easier than the other. In this case, I will probably go for the aromatic compound with the carbonyl, which has one set of alpha protons only. One set of alpha protons only, and on this side, you can put a chloride and bromide. So the 1,4 are not difficult to make. Anolate on one side, alpha bromo carbonyl on the other. Let's finish it with the 1,6. They're not the best one. This one you will see it sounds very, 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 very complicated. And in this molecule, if you need to have a target molecule like that, despite that it's very relatively symmetrical. And yeah, I don't like to say too many carboxyl. It's very offset, off-putting. You have 1,4 dicarbonyl relationships. We have 1,6 dicarbonyl relationships. So you can choose either to go from this direction, 1,6, and you do what is called a reconnection. A reconnection means that you start from the 6-member ring and you need to break it. It's not a disconnection, it's a reconnection because actually you start from the ring and you break it. Now you need to tell me if you remember how to break this ring in this way. It can be DL solder or another way to disconnect and to not to disconnect, to do the synthesis, to use double bond, opening up and forming 2 carboxylic acid on one side. Do you remember any reaction that does that? It's a very cool reaction. I think we did it in the first year or in a bit. I don't know if you did it anymore with John or so. There is a reaction which, when you have a double bond with the right reagents, it opens up and forms carboxylic and carboxylic. But you can do the solder, for instance. Then you can exploit also the 1,4 dicarbonyl relationship that we saw before. And you can use what we did use for 1,4 dicarbonyl. So enolate on one side, alpha bromo ester in this case, alpha bromo carbonyls in general on the other side. This one also has a 1,4 relationship. This one is via 1,6 dicarbonyl reconnector, which can be done via DL solder. in this case, retrodial solder, because we will do the dial solder in synthesis. There is another reaction. If you don't remember, have a look in the books and notes. The reaction is ozonolysis. Ozonolysis is something that partially attacks the double bond. The ozone attacks the double bond, and you can open up using hydrogen peroxide. You can open up and you can form carboxylic groups on both sides of the former double bond. This one, instead, if you choose to go, because the molecule allows you, if you look at it and you choose to go on the 1-4 relationship, it works. So the reaction on the left-hand side is still pretty good. I think it's easier and more elegant, in this case, the reaction with the 1-6. But actually, if you prefer, if it's easier to recognize for you at the exam, and you want to use the 1-4, and it works, and you can make it work, please use the 1-4 because it's easier. Synthesis, if you want to use dial solder, you need to choose the right compound. In this case, it's different from the one that you see on the right-hand side there. I would probably prefer to use this one because it's easier, the reaction, if you do it in the lab, and then you do the ring opening of the anhydride, okay? But eventually it's about the same. So thermal conditions, let's say 200 degrees, the dial solder will form nicely. Then you do ozonolysis, for instance, with hydrogen peroxide, and you open up completely the double bond, and it forms the two carboxylic acid that you need. Then you do ring opening of the anhydride, which is quite easy, either in basic conditions, but also in acidic conditions, hydrolysis, in the presence of water, either in base or in acid, they will do the ring opening quite quickly because there is some strain and the anhydrides are quite easy to open up. Via 1,4 dicarbonyl instead, you can start from this one, but if you want, this is already 1, 2, 3, 4. You can even disconnect any further. But let's start from this one. You do the first reaction with 1,4 dicarbonyl, and you put this one, and then you do it again to form the first part of the molecule. I have to say, there is a little caveat in this one. I have to say that's why I prefer to do the 1,6 in this case, is once you get this molecule, you have this alpha proton and this alpha proton, which have more or less the same acidity. You may argue he attacks these alpha protons first because it's more accessible. This one is very hindered, which is true. So this reaction probably works quite well to form this compound. You might have a little mixture of other byproducts, but this is something you might want to consider. If you didn't have that much hindrance here, I would say that you have a 50-50 mixture or more or less. In this case, probably you will get away with that, and this reaction works really well. And then, if you have plenty of esters, simply, if you want to turn an ester into a carboxylic acid, acidic or basic hydrolysis of the ester always works well. Remember, the difference between acidic hydrolysis of the esters is reversible, so you need to check the conditions quite carefully. This is again if you are in the lab. On the paper, we don't care. The basic conditions instead, they are very sensitive because the carboxylate that you form initially is irreversible. At some point, if you do the hydrolysis in basic conditions, you always need to quench with some water because otherwise you will have a very low, massive carboxylate. Sorry, I cannot speak anymore. Okay. Let's stop here. So we did a little bit of